Welcome to The Explainer. Today, we're diving straight into the absolute core of measuring system analysis. We are talking about the literal foundation of quality in modern manufacturing and engineering. We're going to break down how these systems maintain their integrity, why specific properties matter so much, and, well, what actually happens when things go terribly wrong. Okay, let's dive into this. Here's a quick roadmap of our metrology journey today. We'll start with the high stakes of the measurement world, break down the properties of a reliable gauge, tackle accuracy versus repeatability, look at minimizing errors, and wrap up with the ultimate safeguard, which is calibration. Section 1. The world of measurement. High stakes manufacturing. So in modern manufacturing, the stakes are just incredibly high. We're talking about aerospace components and medical devices where even a microscopic drift can cause catastrophic failures. To prevent that, engineers rely on highly specialized instruments, like this bore dial gauge right here. Notice its anatomy. You've got the plunger that actually contacts the part, the long stem, and the display dial. Instruments like this often boast accuracies of 0.001 millimeters. Now, to put that into perspective, a human hair is about 0.07 millimeters thick. So we're dealing with measurements that are a fraction of a single hair. But here is the catch. To achieve that mind-boggling level of precision, these tools have to be incredibly robust. You absolutely cannot just use basic metals. Gauges require really strict material properties. They use stuff like high-carbon steel, tungsten carbide, or a highly specialized alloy called Invar, and they're often finished off with chromium plating. Why all the fuss? Because they must fiercely resist wear, corrosion, and, crucially, physical expansion due to temperature changes on a hot, demanding factory floor. Moving right along to Section 2, Key Properties of Gauges, Defining a Good Tool. Let's build up our vocabulary a bit and define what makes a good tool. First step is sensitivity. This is the smallest change in the measured quantity that a gauge can actually detect. Think of this as the instrument's awareness level. In critical industries, a gauge must be hypersensitive to catch those minute, tiny flaws before a faulty part makes it into, say, a commercial airplane engine or a surgical tool. Next up is resolution. Now, while it sounds kind of similar to sensitivity, it's actually completely different. Resolution is simply the smallest unit or increment that a gauge can display. It's all about the physical lines on the dial we just looked at. You see, a gauge might be sensitive enough to feel a microscopic change, but if the display doesn't have the resolution to actually show it to the operator, well, that sensitivity is effectively useless. And then we have stability. This is the ability of the gauge to maintain consistent performance over time without any significant drift. Remember those super robust materials we discussed a minute ago, like Invar and tungsten carbide? This is exactly where they come into play. They physically prevent the gauge from warping or going rogue under really tough, everyday working conditions. Section 3. Accuracy versus repeatability. Now, what's really interesting about this next slide is how often these terms get mixed up. Right, so these are absolutely two of the most frequently confused concepts in metrology. People use them interchangeably all the time, but they mean very different things. Accuracy is the degree to which a measurement matches the true accepted standard value. Think of it as hitting the absolute dead center of the bullseye. Precision, or repeatability, on the other hand, is the ability to consistently provide the same measurement under the same conditions. Basically, you can be highly repeatable, hitting the exact same wrong spot 10 times in a row, without actually being accurate. Interestingly, in manufacturing, repeatability is often prized first, because if a machine is at least repeatable, you can mathematically adjust it to become accurate later. Let's put some numbers to this to see repeatability in action. Imagine you program a machine to move to a target position of 10.58 millimeters, and you ask it to do this 5 separate times. Well, because no machine is perfectly flawless, it might actually land at 10.572, 10.568, 10.571, 10.567, and 10.572. To find the repeatability, you literally just find the difference between the most extreme actual positions. Here, 10.572 minus 10.567 gives us 0.005 millimeters. That tiny little number? That is your repeatability factor. And this data here brilliantly illustrates how automation has completely rewritten the rules of production. A conventional, manually operated lathe, it simply cannot achieve true repeatability because it relies entirely on a human operator's physical feel and consistency. But with a CNC machine, a computer numerical control machine, the rate of repeatability is extremely high, which drastically reduces variations from one part to the next. Section 4. Minimizing measurement errors. Automation and protocols. So how do we actually maintain all these great properties out in the messy, real world? Well, let's look at a technical challenge. When measuring the surface roughness of a part, computers use mathematical filters to separate the tiny, microscopic roughness waves from larger waviness. As you'll see in this profile, if an operator chooses the wrong mathematical filter or the wrong cutoff wavelength, they can effectively erase a crucial roughness measurement from the data entirely. The computer will literally tell them the surface is perfectly smooth when it absolutely isn't. To combat these kinds of machine errors, modern equipment uses automated feedback systems. These act as continuous, real-time measuring systems right inside the machine itself. They use sensors called transducers to constantly monitor the cutting tool's exact position and speed. If the tool drifts even a fraction of a millimeter, boom, the transducer instantly sends a signal to the control unit to correct the error on the fly. It's an endless, continuous loop of measurement and correction. But hey, what about the humans? Even with incredible automation, operators are still setting up the machines and reading the gauges. When errors do happen, teams must conduct root cause analysis to figure out exactly why it occurred, not just point fingers at who did it. Sharing those lessons learned across teams is what builds a solid culture of continuous improvement, systematically reducing mistakes over time. Section 5. The importance of calibration. So, the crucial point is none of this, literally none of the tools or properties we've discussed today matters at all if we don't have a way to verify them. Let's look at the core definition here. Calibration is the process of comparing the measurements from an instrument to a known standard to ensure accuracy and reliability. This is the magical link, right here. Calibration is how we take a single, isolated gauge on a dusty factory floor and mathematically connect its accuracy all the way back to perfectly maintained international standards. The benefits of doing this are immense. We've condensed the main reasons into this high-impact checklist. Regular calibration verifies measurement accuracy, for sure, but it also ensures compliance with incredibly strict ISO and FDA regulations, which keeps companies out of massive legal trouble. It detects and prevents the instrument drift we talked about earlier. And, most importantly, it promotes ultimate safety by preventing large-scale production defects from ever reaching the public. We've covered a ton of ground today, from the high-carbon steel of a simple dial gauge to the complex feedback loops of a modern CNC machine. And it all comes down to trust in our tools. So I'll leave you with this one thought to chew on. If a single uncalibrated gauge can compromise an entire production line, how confident are you in the measurements shaping the technology all around you? It's a fascinating, hidden world, and I really hope this explainer helped you see it a little more clearly. Thanks for joining me.